what would a math course be without graphing? We haven't done a lot of graphing. Grade 12 had so much graphing, right? You've probably been wanting to do graphing. I can see it in your faces. Well, one of the nice things about calculus is that it helps you accurately sketch graphs. In fact, it's going to make you graph things faster than you graphed them before. But let's see if you remember. If you had to graph that parabola, y equals 3x squared plus 12x minus 1. Do you remember how you graph parabolas from grade 11? What was the most important point you had to find on a parabola, either in English or French? The vertex, or what's it called in French? Have you forgotten all your French words already? No. There we go. So you had to find the vertex. And how would you find the vertex with this? Complete the square. Remember doing this? You'd factor out the 3, because the idea is you wanted it in this form. And there are either P's and Q's or H's and K's, depending on which textbook you use. And so we first factored out the 3, and then you wanted something squared, but in order to get x plus 2, you see how the 4 tells you it would have to be an x plus 2 squared? You would need to add, a 4 inside of there. But if I added a 4 in there, I have to compensate by doing the opposite. But why don't I subtract 4 here? Why do I subtract 12? Because that 4 got hit by this 3. Technically, by adding 4 inside the brackets, I've technically added 12 to that side. So I had to subtract 12. And then, I have it in vertex form. I would know my vertex is at -2, -13. Spoiler alert, calculus lets us find this faster. And now that you know calculus, you're like, oh, why did I have to learn the long completing the square earlier? Well, that's how math works. You learn complicated math till eventually you get to some really complicated, like derivatives are quite complicated things, especially from the definition of the derivative and all the math. But now we have all these shortcuts. But now that we've developed that, we can go back to things we previously learned and go, oh, well, now I can do this a lot easier. So if we think about graphing this right now, do you know this parabola opens up? Because the a value is positive. And now that you know the vertex is at -2, -13, it looks something like this. And our question that we're going to work on is, how does the derivative help us find the vertex? Well, what is the derivative? The derivative is just the slope of a tangent line. But to keep remembering that that's as simple as the topic that we've done, right? We just have like 22 shortcuts that you've now forgotten 8 of them over the holidays. So just a reminder, some people make like little cheat cards of important things as they've gone through those common derivatives. You might want to make flashcards of those and go through them, because in the next couple of units, certain derivatives we won't run into a lot. Like you're not going to run into the derivative of cosecant inverse very much in the next couple of units, which means that its prime availability for forgetting it is going to go up. You're going to remember the power rule, because we're going to use it a ton. But some of the other ones you're going to start to forget. So make sure, maybe you make little study cards that you go through some of those things that you have a possibility of forgetting, just to glance over them. And that keeps your brain reviewing them. That'll make things easier as we get closer to the exam. Anyways, the derivative is just about a slope of a tangent. At the most important point on this parabola, if I took that point and drew a tangent, what would that tangent look like? It would be completely flat and horizontal, which means it would have a slope of 0. Does it make sense that at any vertex, wherever it is, your tangent's going to be completely horizontal? In fact, on other graphs, at any maximum or minimum, your tangent's going to be completely flat. How hard of derivative is this one? That's about as easy as they get, right? If I did the derivative there, I would get 6x plus 12. If I wanted to find the moment it was flat, I would put 0 in for my slope. Now my question is, how hard is that to solve? That x has to be -2. And you've already found the x coordinate of your vertex. You could plug in -2 into your original equation, and you would find the y coordinate of your vertex. And we just found an easier way to find the vertex of our parabola. Now I'm not saying that, okay, take all of that completing the square knowledge that I have and I should throw it in the garbage. No. But this maybe will be easier. And what's nice about this is this doesn't only help us with parabolas. We can now find max and min of cubic equations. Remember when you graph cubics? In grade 12 they said, and don't worry about where the max and the min is, because you don't need that. You just sort of estimate. Well, now we can find it exactly, so we can draw those graphs more accurately. So, we talked about this. Differential calculus is about slopes of tangents, and these slopes can tell us a lot about a graph. If the derivative is 0, and this is what we just talked about, the tangent line would be horizontal, and we're going to find out this means that your graph is either going to have a local max or local minimum. So if your derivative is 0, you found a maximum or a minimum of a graph. And so much in real life is about finding maximums and minimums, right? Number one goal in life. What's the maximum amount? Oh, not number one goal. Okay. But what's the maximum amount of money I can make while doing the minimum amount of work? That would be a good job, right? My son just said, I just want to not work and make lots of money. Oh, that is, sign me up. What kind of grades do I need for that job? No work, lots of money. I would love that job. Okay? If your derivative is positive, what does that mean? The slope of the tangent would be positive. So if I draw a slope of a line that's positive, we're going to find out that the only way that can happen is if your graph is increasing. We're going to write this all down later. I'm giving away some of what we learn later. Ruining it. Sorry. But if our slope of our tangent is positive, that means your graph is going to be increasing. And if our slope is negative, only way you can draw a tangent point on there is if your graph is decreasing from left to right. And so if we can tell where graphs are increasing, where they're decreasing, where they have their maximums, where they have their minimums, we're going to be able to graph things quite accurately. So we did this already. We could take the derivative, set it equal to 0, plug that in, and instead of completing the square, we get our vertex that way. And in fact, something that you did in inequalities, I'm giving away way too much. I'm just too excited about what's coming next. But something that you did in inequalities is you found out where it was equal to 0. So in this case, it's -2. And then you found out where things were true and false by plugging in values to see if it made an inequality true and false. We'll do something similar to that with our number line. We're going to make a number line for, I guess I'm using y here, y prime. And anything less than -2, if you plug that in, pick a number less than -2. -4, or -6, or -5. And if I plug -4 into my derivative, notice that you'll get -24 plus 12. It will be negative. And if your slopes are negative in a section, your graph will be decreasing. And if you pick something bigger than -2, my favorite is using 0 because it makes mental math easy. Plug in 0, I get +12. That's going to tell us our graph is increasing. Now you knew this parabola. There's -2, -13. You knew this parabola opened up already. But now using calculus, the calculus is telling us the graph has to be decreasing until you get to -2 and then increasing afterwards. Well, that makes sense with a parabola that opens up. But if you got a graph that you weren't familiar with, this would be really helpful. We know that our graph is decreasing until we get to this minimum and increasing after. And in fact, this little sign diagram that we drew here with the decreasing and increasing is really obvious that -2 is going to be the minimum on this graph and not a maximum. Of course, you know this from parabolas already, but this is going to be super helpful when we get to graphs that we don't know. So increasing and decreasing. So if it goes up from left to right, we say that's increasing. If it goes down from left to right, we say that that is decreasing. Makes me curious if in calculus, like we read left to right, but some languages read right to left. Do they have their increasing and decreasing switched? I don't know. Right? Some of you took French immersion. You already noticed there's a few things going from French to English that are like somebody messed up somewhere. Like, let's translate reciprocal to inverse. And let's translate invert to reciprocal. Like, wait a minute. Somebody screwed up somewhere. Right? So if you have this cubic graph, the blue parts are where the graph is increasing and it hits a maximum. And anytime you change from increasing to decreasing, you will hit a local maximum. And then it changes from decreasing back to increasing, we hit a local minimum. So in graphs, we talk about absolute maximums and local maximums. So an absolute maximum, like the parabola that we drew, has an absolute minimum. It's also a local minimum. Because when you talk about something local, you just say, if I took a small little circle around that, is there a maximum in that small circle? Yes. So that's what's called a local maximum. Question? No? Okay. So on this graph, it looks like, if it stopped here, this looks like the absolute maximum. Because the graph ended there. So if the graph is increasing and you draw a tangent, you will always have a positive slope. And if the graph is decreasing, you will always have a negative slope. So the derivative is going to be able to find us our maximums and minimums really easy. It's also going to tell us where things are increasing and decreasing. We call our maximums and minimums stationary points. And there are some stationary points that aren't maximums or minimums. A great example of that is, here's a graph that you know, y equals x cubed. If I find the derivative, that's a really easy derivative to find. It's 3x squared. If I set the derivative equal to 0, can you solve for x for me? Absolutely. X is equal to 0. So that means when I draw x cubed, and you're going to find out that for most of you, you have been drawing x cubed for the last year and a half a little bit wrong. You've probably been drawing x cubed like this. Does that look like an x cubed graph? Looks pretty good. It's not quite right because it should be at 0. If you drew a tangent, it needs to be completely flat. It needs to really flatten out. Here on this one, if I drew a tangent there, oh, my board's a little bit off. It's not 0. It completely flattens out. That's one of the few tangents that actually goes through a curve, right? Most of your tangents touch it and sort of your graph bounces off of it. There are some times that it goes through. Any time where your derivative is equal to 0 is called a stationary point. Stationary because if we brought this to physics, like if I throw a golf ball up in the air, at the moment where it changes from being the top to coming back down, it is at rest, stationary for a second, not moving. Technically on the x cubed graph at 0, it's just like, okay, I'll keep going down. Right? Or I'll keep increasing, but I'm just going to take a break at 0, a little rest, and then keep going after that. So we call those stationary points. Stationary points are a subset of critical numbers. So we're getting into some definitions, new definitions here. We already know maximums and minimums are things that you've seen before. Those are part of stationary points. And then on top of that, stationary points are part of critical numbers. So what is a critical number? It's either a stationary point or a point where the derivative does not exist. These have significant effects on your graph. If your derivative is equal to 0, you're either going to have a maximum or a minimum, or we're going to eventually find that in the x cubed graph. We're going to call that one a stationary point of inflection. But important things happen at critical numbers. If the derivative doesn't exist, sometimes we have a corner or a cusp. Sometimes we have an asymptote from the original graph, because the original graph didn't exist, so obviously the derivative is not going to exist. So something important happens to the graph when the derivative doesn't exist. Something important happens to the graph when the derivative is equal to 0. You're either going to have maximums or minimums, or a flattening out point like the x cubed graph. Sometimes you have a point where the derivative doesn't exist. Like if I took, okay, does it make sense if I took my x cubed graph and flattened it right out? What's the inverse of an x cubed graph? What undoes a cube? Cube root, right? How do you take a graph and do its inverse? You switch x and y's, right? Your x cubed graph looks like this. And technically, at 0 of your x cubed graph, your tangent is straight up and down. And what is the slope of a vertical line? It does not exist, right? So we have a problem there. It's going to show up in your derivative as being problematic at that point. Okay. So I talked about this earlier. Do you remember solving inequalities? In inequalities, if you were to solve this equation, you would set it equal to 0. You would find out where it's equal to 0 by factoring. And then you make a number line. Now in inequalities, if it was greater than, maybe your teacher said use open circles. If it was greater than or equal to, then you use solid circles. Little review of that. And then in inequalities, you then tested it, right? If this is x minus 7, x minus 3, if I plug in 0, which is in this section right here, 0 would give me a negative number times a negative number, which is positive. This section is positive. Do we want it to be positive? Yes, we want y to be bigger than. That's true. That section is true. Between 3 and 7, if I put in 5, can you see this factor would still be negative, but now this factor would be positive. And a positive times a negative will make this section negative. For inequalities, that tells us this section is false. And finally, greater than 7 in inequalities, this would be positive, positive, this is positive. That makes that section true. So in this inequality question, it says solve for this. When is that greater than 0? Oh yeah, I should actually, let me switch that to 0. If you were solving for this, it would be true when it's less than 3 and bigger than 7. We're going to do the same thing with derivatives with the plus and minus, but instead of doing true and false, positive will tell us it's increasing, negative decreasing. So you had these ideas of sign, these are called sign diagrams, figuring out where things are positive and negative. You've done them before, and if you can make connections to things that you've done before, it helps you learn them better moving forward. It's a parabola. So we could complete the square. This one would be very fun to complete the square because it would have fractions involved. Everybody's favorite. Or we could use calculus. So I figure out my derivative. I set my derivative equal to 0 and I solve for x. And x is equal to -1/4. It's a critical number. Critical number is anytime your derivative is equal to 0 or anytime your derivative does not exist. Is there any non-permissible values in your derivative? No. So we don't have any problems in this situation where the derivative doesn't exist. That critical number you could put on a sign diagram. Okay? And we're going to be using lots of these sign diagrams, so what I'll do is I'll make the sign diagram. I'll label all my critical numbers on my sign diagram, and off to the side here, notice how I labeled it as my derivative. In order to figure out where things are positive and negative, it's nice that we've labeled this with the derivative because you're going to be plugging numbers into the derivative. The most confusing part about curve sketching is sometimes you're going to plug a number into the original equation. Sometimes you're plugging a number into the derivative. Sometimes you're going to plug a number into the second derivative. And it's going to get you're going to get, which one do I plug it into? Can be a confusing moment. Okay? So by drawing the sign diagram and labeling the derivative beside, it's telling me, okay, I'm going to plug in 0. What am I plugging 0 into? Into my derivative. When I plug in 0 into my derivative, I get 1, which is positive. I write a positive in this section. This whole section is increasing. I plug in -2 into my derivative. It's negative. This whole section is decreasing. Your derivative sign diagram will tell where things are increasing and decreasing. So it's increasing from -1/4 to infinity and decreasing from -infinity to -1/4. And from this, it's really obvious that our -1/4 is going to be a minimum. Here's our graph, -1/4, -21.125. How did I find this y coordinate? Well, any coordinates that are on your graph, you get from your original equation. So if I plug -1/4 into my original equation, that value will be the y coordinate on my graph. And this is a parabola. You know that this parabola opened up from previous stuff, but now the decreasing part in red, the increasing part in blue. Notice as I go from left to right, I'm going down until I get to the minimum, and then I'm rising or going up after. And as we're going through this curve sketching, I'm going to remind you of stuff from grade 12 and combine it with calculus to help us connect the two ideas. So calculus would say, if you want to graph this, find your critical points. Do you see that you have a product rule here? Keep one the same, derivative of the second one, plus keep the other one the same, derivative of the first one. You could have multiplied this out and then done the derivative that way as well. So you have some choice. Although the x minus 2 cubed, you probably have to use Pascal's triangle to multiply that out, binomial theorem, or you could just multiply it out one part at a time. You might be like, I'll just use the product rule. Okay? With the product rule, it's going to be very easy to see you'll have common factors. You see how I have an x minus 2 squared and an x minus 2 cubed? I can factor out the x minus 2 squared. In the first term, that leaves me with a 3x. In the second term, I would still have another x minus 2. And if I have it factored this way, I get two critical numbers. X equals 2 and x equals 1/2. Calculus says, let's make a sign diagram with those two numbers. So make a number line, put 1/2, put 2. And then on your number line, the number that I would pick less than 1/2 would definitely be 0. And I like to use my factored version as the easiest way to figure out where things are positive and negative. Okay? So here's my factored one. I'll put an arrow here. There's my factored part right there. If you plug in 0, can you see that this will be a negative number squared? In fact, a negative number squared, that first factor, I don't even have to plug in numbers. If you square something, do you realize it'll always be positive? Unless it's 0, but we're not plugging in any of the 0 critical numbers anyways. This will always be positive. If I plug in 0 here, do you see that this is negative? And if I have a positive factor times a negative factor, that section will always be negative. If I plug in something between 1/2 and 1, if I chose 1, for example, this is still positive. If I plug in 1, 4 minus 2, now this is positive, and a positive times a positive number will be positive. That section's positive. If I plug in something bigger than 3, this is still positive. So we have decreasing, then increasing, then increasing. So we can say the interval where it's increasing, we can say the interval where it's decreasing. And this is where we get something like the x cubed graph, where not every critical number represents a max or a min. So, I'm going to show you the graph, and then I'm going to talk about grade 12 pre-calculus and graphing this in grade 12. Okay? There's the picture of the graph. In grade 12 pre-calculus, you would have noticed this as a positive x to the 4 graph. Because if I multiplied that x cubed out and then multiplied it by another x, I would get a positive x to the 4 graph. And in grade 12 pre-calculus, since it's an even number, it acts like a parabola. You would have figured out the end behavior of your graph by memorizing that even polynomials that are positive have their end behavior like a parabola that's positive, up in both directions. Next, since this is already factored out, you would have been able to find this x-intercept, 0, 0, and this x-intercept, 2, 0, and labeled those 2 points next. Okay? And because the x equals 2 had a multiplicity of 3, you would have learned that it flattened out or bent at that point. Remember the flattening out or bending? And if it has x equals a multiplicity of 1, it just goes straight through. So in grade 12 pre-calculus, you would have used the arrowheads that are circled and your x-intercepts to say, I know that it goes down, then flattens out and goes back up. And most likely you wouldn't have gone down far enough because you've been so eager to finish your graph. You probably would have only gone down that far, and we would have said in grade 12, perfectly fine, 100%. Okay? What has changed with calculus? Calculus would actually say, we'd still like you to label those x-intercepts and y-intercepts as much as you can. So 0, 0, and 2, 0, in this factored form, that wouldn't be hard. But now, you don't have to worry about the end behavior thing, because you know that this is a minimum. And at 2, in order for that tangent to be 0, it's going to have to flatten out. So it's got that bend part built into it. And it has to decrease to this one, then increase afterwards. So it naturally gets that shape, but it's more accurate than your grade 12 graph because now our minimum's in the right spot. So we're still going to want our x-intercepts, if possible, from grade 12. Sometimes we can't find the x-intercepts and we're going to be okay with that. But now the increasing and decreasing is going to make us be even better. This is a graph from the end of grade 11, and you also redid it in grade 12. You remember your technique for doing this one? Okay? This is wonderful, right? You've learned 30 different techniques for graphing up till now, and it's like, welcome to calculus. You can throw out all 30 of them away and just use derivatives and increasing and decreasing to make your life easier. Well, what does it look like? Well, here's my graph. I'll change it to a -2 so I can do the derivative. And I get y prime equals -2 over x cubed. It's never equal to 0. However, I have a non-permissible value. X can't equal 0 because then I would divide by 0. So I have no places where it's equal to 0, but I do have a critical point at 0. So it's increasing up to 0, decreasing after 0. And we're still going to use some stuff from previous years. What does a non-permissible value show up on as a graph if it doesn't go away? Right? An asymptote. Non-permissible values are either asymptotes or holes on a graph. If they don't go away, your non-permissible value is an asymptote at 0. The end behavior, you remember that these ones, whenever you had a bigger degree on the bottom, you had an asymptote at y equals 0. Now we're going to talk about vertical asymptotes with limits. What's the limit as x goes to infinity? What's the limit as x goes to negative infinity? Can you see if you put a very huge number in for x, it would go to 0. And so that shows up as our horizontal asymptote. Now with those asymptotes in place, the only way you can draw a graph with no x-intercepts, no y-intercepts, increasing would be to have it in this section, and decreasing to have it in this section. In grade 12 pre-calculus, you actually plugged in points to get those points to see which sections it would be in. The increasing and decreasing, the only way possible to do that would be to draw it as we have here. This was like the volcano graph in grade 11, I called it. So all of your graphing techniques can be still used and still helpful, but they can be replaced with calculus. But now we get to something that we would not have been able to graph in anything we've done so far. Do you remember what graphing technique you use when you have no graphing techniques to use? Let's see. What is the very basic graphing technique? Table values. You just keep throwing in x's until you if you have 100,000 points, you'd have a pretty accurate graph. The problem with table of values is it just takes, right, if every point took you a minute to do, 100,000 points would be a long question. So let's set this up. Let's find our derivative. Okay? Let's set it equal to 0 and solve. We get x equals 1 as a critical point. We also notice there's a non-permissible value in our derivative. X can't equal 0. Those are both critical points. We set up our sign diagram with both of our critical points. And again, you choose a number in the section, and I've labeled it with the derivative, so we plug it into the derivative. So if I plugged in -2, maybe -1, because I can cube root -1. Cube root -1 is -1. This will be positive. 2 plus something will be positive. And you see, you're not concerned about actually getting a value. You just want to know, is it positive or is it negative? So when I plug in, mental math-wise, if I plug in 1/8, cube root of 1/8 is 1/2. This will be 2 minus 4. That's a negative number. I'll get that section to be negative. So we know there are 2 intervals where it's increasing and 1 interval where it's decreasing. Notice we use round brackets when we say where things are increasing and decreasing. Because at 0 and at 1, those are critical points. They might be maximums, they might be minimums. In fact, from here, can you see on this graph that it sure looks like maximum and minimum? This one I'm a little bit concerned about because it was a non-permissible value. We type this equation into our graph, and in this case it is actually a maximum. It's a cusp. It goes to a sharp point. The blue part, okay, is increasing. Can you see your brain tricking you in this situation? The arrowhead on the graph makes you, if you see this part here, can you see, you want to say it's going down, you want to say it's decreasing on that left side? We say increasing or decreasing by going from left to right. From left to right, the graph is going up. But with that arrowhead on there, your brain would be like, oh yeah, definitely going down, definitely decreasing. And you see yourself mixing that up a little bit. Remember, we're going from left to right. If you had, right, oh, there we go. You were traveling. This is you, wow. Now I want that to go away. Okay, I can do this. This is you. And if you were going from left to right, look at you're going up. Get to this point you're going down, and then we're going up again. So we have to think of something going from left to right. But when our brain looks at this graph, our brain sees the arrowhead, you're going to want to say that right-hand section is decreasing because it's going down. Be careful. No asymptotes, because if you look at the original graph, there are no non-permissible values in this graph. But we just were able to draw something that hasn't ever existed before. And we would know that there would be a sharp point. There's no derivative on a sharp point because you can draw so many tangents on a sharp point. But the graph is still continuous all the way through. So these are graphs that we were not able to do in grade 12. And now just with simple calculus, we can get a pretty accurate idea of what's going on. So this one too, we take the derivative. The derivative again has a non-permissible value. We solve the derivative, and this time we get plus or minus 1 as a possibility. Set up your sign diagram with your derivative. And again, to get the positives and the negatives, you're plugging in values in those sections into your derivative. Right? So if I wanted to find out this is negative, I would plug in negative 1/2 for x. Okay. If I plugged in negative 1/2 for x, I plug it into my derivative. This will be positive 1/4, cube root of 1/4. Ooh. It gets to be a little bit of tricky mental math. You might need a calculator, or you might choose, might try to choose values that you can actually cube root. But they are sometimes hard to find. So cube root of 1/2, and then I'm doing 1 minus that. Maybe you'd realize that if you cube root 1/2, you're going to get something less than 1. And then when you do the reciprocal of that, you get something bigger than 1, and then 1 minus that becomes negative, tells you that section is negative. Okay? If it's too hard and they let you have a calculator, well, if they let you have a graphing calculator, then just graph it right from the beginning. That seems smart enough to do. And each of your values, -1, 0, and 1, each of your critical points, to find the y-coordinate, well, y-coordinates or points on your graph come from your original equation. So I'm going to plug in -1 into my original equation. I'm going to plug 0 into my original equation. There are no non-permissible values in your original equation, which means your graph is going to be continuous all the way through. Here, we're going to have a maximum. Here, we're going to have a minimum. Here, this is the non-permissible value. That's where things get interesting with critical points. In this situation, it just got extremely steep at 0, 0, so that your tangent was vertical and did not exist. The last one was a cusp or a corner. I think it was a cusp. Remember the difference between a cusp and a corner? Have I ever told you the difference between a cusp and a corner? That's a corner. That's a cusp. On a corner, the limit from both sides would have different slopes going to both sides, whereas the limit of the derivatives are both going to be vertical on this one, so they're kind of the same. I think that's the technical difference between a corner and a cusp, but I might be technically off a little bit. You won't be asked corner or cusp, which one is it? Okay, we have time for one more. find the critical numbers for this graph. So I'd like you to do the derivative and find out all the critical numbers on your own. You see, it was a product rule. And what's going to be really helpful for finding critical numbers is, especially in product rule, after you've done the product rule, you will always have parts that will have a common factor, even though it's a binomial, that you can factor out. So I can take an x minus 1 out. I can also take, oh, here I did that. Yeah. I might do that first. I did at the end. I can take an x minus 1 out. I'm also going to have to use my skills with getting things to be a common denominator. So this x to the negative 2/3 would be an x to the 2/3 on the bottom. So I get a common denominator over here, which ends up getting a 6x. I have a non-permissible value at x equals 0. The top is now factored. So my critical numbers are at 1, 1/7, and 0. This is what that graph is going to look like. So we can find the values. You'd have to use your calculator, obviously, with the 1/7. But you can find your y values by plugging those critical numbers back into the original equation. We could have done a sign diagram to find out where things are increasing and decreasing. And at 0, 0, the non-permissible value, it's straight up and down at that moment.